We're now going to look at something that's commonly called shifting. It can also be called rigid and non-rigid transformations. But basically, we want to look at how to take the graph of a function and move it around. Now, for our example, we're going to work with quadratics. And to make this example as easy as possible to follow, I want to start off with the easiest possible quadratic, and that is the y equal x squared. So I'm going to go to the calculator, and on the y equal to screen, I'm going to put in the x squared, which should be the parabola graph that we are most familiar with. And what we want to look at when you're talking about shifting or transformations is how you go about taking a graph and moving it left or right or up or down, leaving it right side up or turning it upside down, make it thinner, make it wider. So we want to take a look at that, and we're going to take a look at first of all our left and right movements. All right, so given any function f of x, if you know what it looks like, and our f of x is going to be the x squared graph, the first thing we want to do is see what happens when you multiply it on the outside by a constant, and that's the role that the a plays. Now let's go with an easy constant to begin with. Let's go with a -1. So I'm going to come down here, leave the original x squared graph where it was, and put in -1 times x squared, and see what happens. As we can see, the result of the -1 is that the graph is turned upside down. All right. So our first conclusion is that for our quadratics, that when a is greater than 0, the graph opens upward. When a is less than 0, the graph will open downward. Basically, applying this to a greater family of functions, we would say that when a is less than 0, not less than -1, when a is less than 0, when you multiply a graph by a negative value, it implies a reflection across the x-axis. And that's what we saw here. Multiplying by a negative number reflected the original graph across the x-axis. Now, as far as the a is concerned that you multiply by on the outside, there's actually more that we can do with this. If we go back, get rid of the second graph, and go with a different a value, say maybe a 3x squared instead, then what we see happening is the graph is going to become much thinner. So this is because an a value greater than 1 is going to create a vertical stretch. All right, and again, we see in the graph that this graph has been pulled up vertically, making it thinner, and that is the result of the 3. Now, if we were to go back yet again and take the 3 and replace it with a 1/3, and you can try different values on your calculator and you'll see the result for yourself. Again, the original graph is drawn and a wider graph shows up. So an a value between 0 and 1, we don't want to go below 0 because that causes reflections, calls a vertical shrink. So we can see shrinking and stretching occurring because of certain a values, and we also see reflections across the x-axis occurring because of negative a values. So if we were to compare y equal x squared to y equal -1/5 x squared, we see the negative causing the reflection. We see the 1/5 causing the shrink. So these two components actually work independent of one another. Now let's look and see what would happen if we were to add or subtract a number inside the function. So we're going to a new category here. We're going to go to f of x plus or minus, and we don't want to use a b here because b means something else. It's a part of this original quadratic, so I'll just go with an h. So let's see what happens when we add or subtract a number inside the function. Going back to the y equal to screen, clearing out what was there, putting up some parentheses, and we'll go with x plus 3 for starters. Don't forget to close the parentheses. Don't forget the square because it is quadratic. Now when we hit the graph button, we see the graph has been moved. And specifically, it's been moved horizontally to the left. So that means that for a x minus h, this is going to be a left-hand movement. And let's go back and see what happens when instead of, oh, I'm sorry, I wrote that one backwards. For an x plus h, it's a left-hand movement. Let's try again and see what happens. I wanted to check, see what happens with an x minus h. Does it move it in the opposite direction? And it does. So, for an x minus h, that is a right-hand movement. And what you will discover is whatever happens inside the function versus what happens outside the function, it's the opposite of what happens inside versus outside. In other words, if you had a y equaling a negative 3 times an x plus 5 quantity squared, here's what's going to happen. The negative is going to reflect. The 3 is going to be a stretch. And the plus 5 will not go right 5, but left 5. Again, inside it does the opposite of what you're going to think it's going to do. Now, if we were to look at f of x plus or minus a k value, in other words, add a number outside the function instead of inside the function, we're going to see something entirely different happen. If I take x squared plus 2 and graph that, we see that the function has moved again, but this time not left, not right, but up. So what we're seeing is that an x plus k is going to be an upward movement. And, of course, best way to write that, I guess, would say x squared plus k, to clearly show the k outside, and an x squared minus k is going to be a downward movement. I'd be willing to bet we can try that real quickly and find out. Go over and change the plus to a minus, graph that, and instead of moving up, sure enough the graph moves down, as we can see here on the main display. So basically what this means is adding and subtracting inside is left and right movement. Adding and subtracting outside of a function is up and down movement. Now, what does this imply for us as far as our quadratics are concerned? Well, we can basically, with any quadratic there, if it's in the right form, from shifting, we can tell where our vertex is. All right? So if we had y equaling negative 1/2 times an x plus 7 quantity squared minus 8. Remember, for our original x squared graph, your vertex is at the origin, or in other words, 0, 0. So in this new quadratic, we see that the negative has reflected it across the x-axis, which didn't affect the vertex. The 1/2 has caused it to shrink vertically. That didn't affect the vertex. But here's what we do see. We have moved, because of the plus, we have moved left 7 units. So the vertex is now at -7. Then we went down, because of the minus, to a -8. So the vertex has moved from 0, 0 to -7, -8. In this form, that's easy to spot. You know exactly the location of the vertex. You can tell. Problem is, though, sometimes we run into quadratics and it's not in this vertex form. So how do we get it there? Well, the easiest way, the pencil and paper technique, is completing the square. Let's say we had f of x equaling x squared plus 8x minus 9. Well, we need to complete the square so we can get it into the vertex form. Remember, your vertex form is going to look like this. Y equal to a times x minus h, quantity square, plus k. Now, why is it a minus in here and a plus out there? Well, remember, inside it does the opposite of what you think. Outside it does exactly what you think. In other words, a minus inside isn't left, it's right. A plus isn't right, it's left. Outside, a plus is up and a minus is down. And again, that's why it's written that way. So we need to take this and make it look more like that. And here's how we do it. We're going to take the x squared plus 8x and sort of separate them from the minus 9. When you complete the square, remember, you take half of the b. So we're going to take 8, cut it in half, and then you square. So we're going to add a 16 right here. The reason we want to add a 16 there is so that this can be factored. Now, since I'm adding 16, and I don't want to change the actual function, I will simultaneously subtract 16 off to the right-hand side where it's out of my way. This becomes x plus 4 quantity squared. Factor it for yourself. You'll see that's what you get. Minus a 25. So the plus 4 means left 4. The minus 25 that means down 25. And there's your vertex. And there is the quadratic in vertex form. I think perhaps now let's look at our next example. Let's go with f of x equaling x squared minus 10x plus 12. Again, to complete the square, I group the x squared and the 10x together, move 12 over out of my way. I take the 10, I divide it by 2, and I square, which is going to be 5 squared, which is going to be a 25. So I add the 25, and I subtract 25. Not a 12, but a 25. Again, why adding and subtracting? To keep the actual same function, but in a different form. Now this, again, will factor, because what I've created is a perfect square trinomial. And this time it's going to be an x minus 5. And again, where did the 5 come from? Just like the 4, from right here. It's the number you originally squared to get the 25 or the 16 in the first place. So that factors easily. Now 12 minus 25 is going to be a minus 13. So again, the minus means right, not left. The minus here means down, not up. And so your vertex will be at 5, negative 13. And you've got it in vertex form, so you can easily see the location of your vertex. Now the only thing about this is it can get a little bit more difficult when this number isn't even. So let's try one last example with f of x equaling x squared plus 5x plus 4. Alright, so again we group together those two terms, move the 4 out of the way. We're going to take half of 5 and square it. Now I encourage you, don't go with 2.5. In other words, don't go with decimals. Don't go with mixed numbers. Keep it an improper fraction, because the improper fraction form is the easiest form to square. So it's 25/4 that I will add and in turn subtract. Again, this part is easy to factor because I know what it was before I squared. Now, if you think you're going to have any trouble with this subtraction problem, we can jump straight to the calculator. We will key in the 4 minus 25/4. Of course, the calculator is going to give us a decimal answer, but we can ask it for a fraction. So when we ask for a fraction, we get this -9/4. We go back and we say -9/4. Now we are in the correct form for the vertex. The +5/2 means left, so it's a -5/2. The -9/4 means down, so it is a vertex of -5/2 and -9/4.